Okay, so for number 41, radium 226 has a half-life of 1,599 years. Now, every single exponential growth and decay problem that you'll ever get, you're going to use y equals c e to the kt power. Now, do we know anything else besides that? It's that the problem says, what's the percentage 100 years later? Well, let me ask you this. At year 0, so when t equals 0, what percentage do you have? You have 100% of radium 226. That's another way you can write it. Now, this is our initial value, 100%. So I can actually say c is equal to 1. Or you could have put 100 if you wanted to represent percents. I use 1 because it's easier and then I don't really have to multiply by anything. If you put 100, you have to multiply by stuff. So y is equal to 1 times e to the kt power. Because that 1 represents 100%. Now, whenever you're doing these problems, we have to either figure out c first or we have to figure out k first. And if you're given c, you figure out k and then you solve the problem. So we had to kind of think a little bit to get c, which was 1. We just use that as 100% since we're dealing in percentages. So now let's do this for k. The only thing that we know is that y is going to be equal to 0.5 because it's going to be equal to half of the original at t equals 1,599. So I know this is going to be 0.5 is equal to e times 1,599 times k. And I got rid of the 1 because multiplying by 1, it doesn't really matter. Now I'm going to show you something really cool in a second here. Now, how do we solve this type of situation? Yes, natural log of both sides. So I'm going to take the natural log of 0.5. That's going to be equal to the natural log of e to the 1599k. Now, natural log of e, what happens to that? Yeah, they're gone. So I'm left with the natural log of 0.5 is equal to 1,599k. Now solving for k, 1599, 1599. So k is equal to the natural log of 0.5 over 1599. Now let's take a look at this before we move on to the actual problem. Yes? Since we're doing a half-life situation, we're using this situation. That if we're starting with 100%, we're going to get 50%. So this is 50% at 1,599 years. So we're going to use that. Whenever you're doing a half-life problem, you're going to use that like ordered pair almost, because the ordered pair would be this. We're going to use that to figure out what k is. But even better yet,
I didn't want to interrupt you.
okay, you scared me. Even better yet, take a look at what k is. What do you think this 0.5 represents? Yeah, half from your half-life. What do you think this represents? The 1599. Yeah, the half-life years. And this is actually something that you can use all the time. You can almost skip this entire process, and for half-life, k is equal to the natural log of 0.5, because you're going to have half, over the half-life years. So whatever we're told is going to be our half-life, you can almost skip right to this k. Because no matter what, it's always going to end up being the natural log of 0.5, which is your half, and how many years it takes to get to that half. So in this case, that's our 1,599 for radium-226. If it was for something else, then whatever the half-life years would be, that's what we would be able to use. So that's one of the really cool things about half-life, is our K becomes something easy to use. It only works, though, with half-life. But I wanted to show you that anyway. So I got my K. I can go back to the original equation, y is equal to e to the natural log of 0.5 over 1599 times t. And then what did it say after 100 years? So I want t equal to be 100. So I plug that in, and y was equal to, just, I'll let you guys play around with the calculator, 95.76%. So there's only less than 5% left over. Or less than 5% has decayed after 100 years. Yes, sir? Works. What did you do different? Alright, so you did the 0.5, and you said you raised it to the 100. Oh, and then times 100. Interesting. And it worked out good for you? Interesting. I've never seen it. Honestly, I've never seen it done that way. But cool. Hey, it worked. That's the important part. That's cool. I like that. I'll have to research that a wee bit more.